What I was trying to tell you is that if you have imagine you apply. So what happens when you have electric field, apply electric field, and you have electric field in this direction, and a charge which is a positive charge. Then what happens? It feels a force, net force, in this direction, and it starts moving along this line that you can imagine. So this is the movement that you, and if it happens to be this is case 1. So if you think of an electric field and you have a negative charge, then it feels a net force in this direction. Okay, force, electric force in this direction, and it starts moving in this direction. So this is the way we understand the thing happens as starts moving if it is a homogeneous electric field. So in this direction, negative charge, this is a negative charge, it starts moving in the opposite direction. It has, and if it is a positive charge of the same magnitude, it will move along this direction. Okay, so now the third case, so this is a case 2 that we can imagine. Now in the third case, what I am going to show is that case 3 is that you have electric field and you place a system which is composed of one charge like this, Q plus, Q minus connected. So what will happen now? There will be a force acting on this direction, force which will act in this direction, थोड़ा सा ठीक है, force, and a similar electrostatic force you can think of, which will act on Q minus in this direction. So this is a dipole, we can say electric dipole. So in this manner, if you think about it, then what will happen? The net force in this, so this force is in opposite direction and equal in magnitude. So overall, if you find so the net force will be sum of these two is sum of the F on Q plus, F electrostatic on Q minus. So sum of these two things, and this is one vector cancels out the other, so net force is 0. But the overall effect is that, so there is no net movement along a line, but the thing starts rotating in this direction. So there is a but there is a net torque, what we call as, it will start rotating in that field. So ये electric field इस पे लगा है, so it will start rotating because of there is a torque tau, which is given by what we know as the dipole moment. Dipole moment को अगर हम so we can represent it by P cross, so dipole moment into, so this is a torque which is also given by PE, where P is the dipole moment, where P is dipole moment. ये distinguish करने के लिए थोड़ा सा लिख रहे हैं इस तरह से, dipole moment, and E is the electric field, or you can write PE sin theta. ठीक है, so this is what happens. It starts rotating around it, and when it is the dipole moment gets aligned with the electric field, it is stable, energy is 0. energy is lowest, and that is the happy situation. It will happen. So in a similar thing, you can replace these things with magnetic field. And in a magnetic field, you cannot think of if you have a magnetic field, you do not have a magnetic monopole. So all these things are not possible. You only have north pole and south pole. So instead, if you are thinking of what will happen, a similar thing will happen with so this force is this is not this is N. If we talk about, so instead of think about a bar magnet, think about a bar magnet. So it is something like this, and north pole south pole, they are connected. So something like this will also happen. This is magnetic force on the both poles are equal. Again, net force here will become 0 because of the two poles. The action, the force will be equal and opposite in direction. So what is going to happen is on north pole and plus force magnetic on south, both are equal in magnitude, opposite in direction. So there is again I'm going to replace this with mu for magnetic, and this electric field is replaced with magnetic field, and a similar relationship emerges for torque. And so torque is this mu b sine theta, where mu is your dipole moment. So just like you had electric dipoles, here we are talking about magnetic dipoles. Okay, and magnetic dipole. So the same effect will be there when I place a bar magnet. A bar magnet is a magnetic dipole, and similar thing happens. The overall force is 0 on if we count the north pole and south pole, but there is a net torque. Torque is there, so it starts rotating until it gets aligned with the field. So the natural tendency would be something to align with the field. Whether if you have an interactive system of a dipole, whether it's electric dipole, whether it's magnetic dipole, there is a tendency to align with the field so that the energy becomes minimum. Okay, because of the torque has effect. So a force, fundamentally from physics point of view, whenever you have a force acting on a substance, it will move in that direction, like a linear fashion, you can say. And if you have a torque acting on it, it will start rotating in a circle. There will be no net movement from one of the overall the system that you look at, but that around that same place it will start rotating. So that is the torque that we are talking about, and the torque tends to align with this vector that we are talking about, the dipole moment, whether it's magnetic dipole, whether it's electric dipole. अगर मैग्नेटिक फील्ड होगा तो मैग्नेटिक डाइपोल इंटरेक्ट करेगा, अगर इलेक्ट्रिक फील्ड होगा इलेक्ट्रिक डाइपोल इंटरेक्ट करेगा. लेकिन द इफेक्ट विल बी वट एवर द फील्ड इज, interaction happens, and there is a tendency to align with the dipole tends to align with the field. When it is perfectly aligned, the force is 0. Force is the force torque will become when sine, if it gets aligned, the torque will become theta will be sine theta is 0 when angle is 0. So that way you can think there will be no torque and the system is in good thing. So just like if you have linear frame of mind, you know the force is defined by this so you have this thing, so the work done in this case, so if something is uh, not aligned and you are trying to move it from, then the work done will be given by torque into d theta. So angle, from an angle of so from here we derive it, and you get to see when you calculate this thing, you will get, if you work it thoroughly, from any arbitrary angle to making it align with the trying to, so if it is perpendicular, the force will be maximum, and trying to align with the field, that then you have the force, sorry, the torque will be decreased, and finally it will be least in case of this. So accordingly the work done can be calculated, and which you can find out if you do the calculation. It is a simple class 11-12 problem for a bar magnet. You can, so basic idea you have to catch up, that when you try to do this and work out the thing, rotate it from a direction perpendicular to the field, to any given direction, the potential energy stored in the system is given by the work done, the difference of work done in the two cases, theta and pi by 2, and that gives you a negative sign over here like this. So something like this. So potential, when it is the so equilibrium condition, you have so if it is aligned, so this is the direction of the magnetic moment. So here m is the magnetic dipole moment of the magnet, डाइपोल मोमेंट ही होता है, मैग्नेटिक मोमेंट और कुछ नहीं होता, वो भी डाइपोल मोमेंट ही है. मैग्नेट्स एग्जिस्ट एज डाइपोल्स, नॉर्थ पोल साउथ पोल डाइपोल है, उसका मोमेंट है. सो टू पोल्स जहां भी होगा चाहे उसको डाइपोल कहेंगे, ठीक है. इलेक्ट्रिक फील्ड हो इन टर्म्स ऑफ चार्जेस, और इन टर्म्स ऑफ this magnetism we say north and south pole. So this is a dipole moment that we are talking about. So you always get it in terms of you if you work out the details by yourself, you will find that it turns out to be negative like this. And this is was the starting point in our discussion, that it is given by the dot product of magnetic moment into the magnetic field. So dipole moment, magnetic dipole moment of the magnet, or simply said dipole moment of the magnet, we call it in short magnetic moment. So I told you that there's another point to think, is that, so this is the basic idea. We start from here. So everything when it tries to align, torque is minimum when it is aligned with the field. If it is opposed to field, then torque will be high if you calculate it somehow. So there will be some energy. So energy can be calculated like this. So something like this. So you will find these things in your class 11-12 books. So you can just freshen up your things from there. So the main point is that there will be no net force, there will be a torque, and torque is given by this moment, magnetic moment into the sine theta like this, and work done can be calculated then, and you find the work done theta 1 theta 2 something, you will get this thing done. So from that thing we start, and that is how we calculated the energy. And so here one more important point to be kept in mind. I don't know whether I told you previously or not, but so electric dipole versus magnetic dipoles, an interesting point. So फंडामेंटल अंडरस्टैंडिंग इज नेसेसरी. आप एनएमआर सब सॉल्व करने लगेंगे, अब दिक्कत क्या है, देखिए थॉरो होने का मतलब यही होता है कि आप फंडामेंटली स्टार्टिंग से सब कुछ समझ रहे हैं. तो आप एनएमआर का प्रॉब्लम स्पेक्ट्रम सॉल्व कर रहे हैं, लेकिन आपको मैग्नेटिक मोमेंट डाइपोल ये सब नहीं पता है. So that's something that you are not being thorough in that. So sorry, so this is something you have to pick up. So electric dipoles and magnetic dipoles, fundamental difference है, both are dipoles, there are two poles in both of them. लेकिन if you have say q plus q minus, two are connected by a rod, something like this, two charge particles. When you break it, so this is a dipole, and when I try to break it, it will break it into a positive charge and a negative charge. So it splits into so an electric monopole. So this q plus q minus जो एक point charge कह रहे हो, so this is these are electric monopoles. So this is electric monopole, this is another, so it will break up. So one having positive charge, one negative charge, it will break into another monopole, electric monopole. Now think of a magnet in a similar fashion. You think of a magnet and north south, try to break it. So you have a piece of magnet, a bar magnet, you try to break it into pieces, break it in pieces, you will get it, you will still get, when you break it, you still get, sorry, I'm not, to the scale drawing is not done. So you will still get two pieces of the rod. If you have an iron rod which was magnetic and now you have broken down into pieces, you have north south, so it is, and go on repeating, go on breaking, every time repeat it, you will always have small north south, multiple pieces like this. So practically it has been found that there is, so we go to the tiniest of particle, it is still a magnetic, in the magnetism, in the terms of magnetism, it is still behaving as a dipole. So so you break a larger magnetic dipole, you always get a dipole, magnetic, you get a smaller magnetic dipoles. So you are getting a large number of magnetic dipoles, magnetic dipoles. So this happens to the tiniest of particle. You go एक electron तक पहुंच जाओ, an electron which, so in a sense of that, what I am trying to say, large number of magnetic dipoles, no monopole is formed. It will always be a magnetic dipole. Magnetic monopoles do not exist, practically not. So now think of in these terms. Suppose you had this q plus q minus that I was talking about, it is positron, so E plus, and suppose it is E minus. It is, suppose if I can hypothetically, let's imagine something like this happens. When you break it, there will be electron and this will be positron. So this is a electric monopole, But if it is having a spin, because of spin or due to a motion, what will kind of thing it will generate? Is it a magnetic monopole? No. So is a moving electron, so you know by 11th 12th knowledge of that a charge which is moving will generate magnetic, will have magnetic moment, and it should be attracted by thing. So what do you think? A moving electron, is a moving electron a magnetic monopole? Is it? No, it is still a dipole. So electron, which is a fundamental particle, when put in a magnetic field, spinning, it has spin, it has orbital motion, or it is due to anything, whenever there is some classically you know about it, a moving charge will have some will behave as a magnet, and this is still so electron will always, it is also, it behaves as a a tiny magnet, and that tiny magnet is a magnetic dipole. It is still a magnetic dipole. ठीक है, तो जब भी हम उसको इमेजिन कर रहे हैं इलेक्ट्रॉन्स को, दे या इट इज अ मैग्नेटिक डाइपोल. ठीक है, उसमें भी नॉर्थ साउथ पोल की तरह आपको एक इमेजिनेशन लाना है, and then you start working out the details. Okay, so the way I told you, like yeah, so you have so you can imagine something like the bar magnet picture is in your mind always. So you can always imagine that when we talk about electron and talk about the direction of magnetic moment, it is this that we are imagining. We are imagining a south pole, we are imagining a north pole, and that the direction of magnetic dipole is from this south to north. So like that you have to think. So this is what we tend to think. Okay, so mm, so just the way we had, like, I think when we were discussing spin orbit coupling or something like that, we had when I had discussed, किस नाम से सेव किया था मैं भूल गया. LS coupling, अच्छा, yes, I think this one. When I discussed this thing, then I probably discussed this part. No, not in this one. मैं भूल गया किस नाम से सेव किया था मैंने. पिछले सेमेस्टर जो पढ़ाया था, in last semester I had discussed सॉरी, कोई बात नहीं, कहाँ गया उसमें. एक्चुअली मैंने पिक्चर जो डाला था वो इम्पोर्टेंट था. लिगेंड फील्ड थ्योरी, टर्म सिंबल के नाम से होगा. So when I discussed these things, I probably told you, yes, this is what imagination, you have to stretch your imagination to this level. See, so this orbital motion, and due to if you think of orbital motion, and also the spin is always associated with an electron, whether it is part of an atom or not. So spin will always be there, just like mass. So because of this, this is your imagination. So this is electron, the first picture that you see. So put a bar magnet here, like having a north pole and south pole, and this is the thing. This is your the direction of your magnetic moment that you are talking about, dipole moment of this. So an electron is a small magnet, and that magnet has two poles, north and south pole, so it is still a magnetic dipole. Okay, it is a magnetic dipole, and this is the direction that we are talking about. So now, because if you have a positively charged proton, p plus, so when you are talking about the direction of dipole, it will be different. So if electron is pointing like this, instead of this, if you have suppose for a moment that instead of this, if you have a proton, then the direction will be reversed. So this kind of imagination should be there. And suppose I think I have discussed some points. So in a similar way, if I have what I'm saying, so if you have a proton, imagine a proton also has a spin. uh, Proton has spin, so the direction of magnet, so if it is in the same fashion, if I put it, sorry, कहाँ गया, हाँ, so ये ऐसे ही सर्कल करता हुआ अगर प्रोटॉन होगा स्पिनिंग के साथ, this is the spin that we are anti-clockwise spin that we are showing over here. So if it is giving this kind of, so you apply so you have a vector. So if this is you are applying right hand thumb rule, so it is giving you a direction that is pointing down, so the vector is pointing up. But in this case, if a proton is having a same kind of movement, like this, similar motion, then the vector will be like this. So whatever you have for whatever direction this is, so it is in fact the vector that you angular momentum vector is pointing downwards, and this is the direction of angular momentum, and this is the direction of your so spin angular momentum. You apply right hand thumb rule, you can see, and you curl your fingers, your thumb will be pointing downwards, is it? So that is the direction of spin angular momentum, and this is the the magnet is pointing up. So this is because of the having a negative charge, the behavior is opposite, and you have thing like this. So but and proton will be having so it has the direction of spin angular momentum. Spin angular momentum will be pointing downwards, and the magnetic moment, the north and south pole, so this will be pointing downwards too. So this is the difference between proton and electron, a positively charged fundamental particle and a negatively charged particle such as electron, that both will behave as tiny magnets. The fundamental difference is that if we assume the spins to be in a particular direction, like clockwise or anti-clockwise, for an electron, uh, for proton, the direction of spin angular momentum, will generate a magnetic moment which will be directed along the same direction. But for electron, the direction is reversed, and it is having like this. So this is something that you have to keep in mind. But remember, when we apply magnetic field, both the magnets, any magnet will try to arrange its magnetic align with the field. We say to having a lower energy, there will be tendency to align with the field of the applied magnetic field, and there is always that tendency. And that's how we, if you see the pictures now which we were discussing, you can probably understand those things, so why it is something like this. Okay, so where we were, yeah, so now we are here. So this was the point that we were trying to make. So now I told you that we have yes, this is spin angular. So for electrons, you have spin angular momentum. If it is electron is moving like this, the angular momentum, apply right hand thumb rule. So curl your fingers along this arrow like this. You are getting thumbs up, like, right. So this is your spin angular momentum. So the magnetic field, the magnetic moment will be there, which will be, so this spinning electron behaves as a magnet, and its magnetic field lies in the opposite direction. Similarly, the same applies to this orbital motion also. You can think of the electron is also undergoing this motion in this path. ये सर्कल, बड़ा वाला सर्कल जो आप देख रहे हैं, उस पाथ में मूव कर रहा है, and when it is moving, it will have this orbital angular momentum. Sorry, excuse me. Yeah, so this is the orbital angular momentum, and so you can curl your fingers along the line indicated. So it is like this. So curl your fingers in this direction. Your thumb will be pointing up. So that makes sense. So orbital angular momentum, and this way, this is also, so this is your magnetic moment. The green line is the magnetic moment generated due to this motion, orbital motion, and this is also pointing in the opposite direction. Remember, if we apply same thing for proton, if we imagine a proton having the same spin, proton being a positively charged, the direction of the two things, the spin angular momentum and the magnetic moment, will be same. But here the minus, due to the negative charge of the electron, you are having the magnetic moment points in the opposite direction. So what I told you, that this magnetic moment, that is the moment of the magnetic dipole. Here what we say, moment of the magnetic dipole. What is this magnetic dipole? This magnetic dipole could be my, what is this? This is a spinning electron. So this, if I assume this, then this magnetic dipole mu is equal to, is directly proportional to the spin angular momentum, which is denoted by S, small s. When I am this if the magnetic dipole is the orbiting electron, then I indicate this mu as being proportional to orbital angular momentum. Okay, so the magnet that I am viewing is a magnet because of, for two reasons: due to spin, due to orbital motion, and we have different reasons. So we assign this thing. When you remove the proportionality constant, you have the constant that comes up is gyromagnetic ratio here, and due to additional factor that I told you in case of spinning, the relativistic considerations comes into picture, and because of that there is additional factor, G factor of 2. So this is the G factor, we call it the due to relativistic effect. So actually the magnetic moment due to the spinning is much larger than as compared to the orbital one. Relativistic effects. सो जो इलेक्ट्रॉन का स्पीड होता है वो बहुत ज़्यादा हो जाता है अगर आप एक पार्टिकल की तरह उसको विजुअलाइज कर रहे हैं, and the particle, imagine if it has to maintain this momentum of each half under root, so to maintain that kind of speed, it will be very much greater than speed of light, so something. So when that is an exhaustive calculation, we are not going to that, but due to that factor again you have to due to the linear velocity becoming almost comparable to speed of light, in fact greater than that if you consider it as a particle, that happens, and because of that you have a G factor coming into picture. So actual calculations shows that it is twice from, so theoretically expected is mu E into S, right? But practically calculated, it was found that it is twice than what we were expecting, and that's why this term G factor was introduced. Okay, and later on calculation, relativistic calculation confirmed that yes, it is due to that effect. Okay, so we have fundamentally we are clear on this part, then we can move forward. And now, so any magnetic moment which is aligning itself, oops, why this happening, कट क्यों जा रहा है, अभी भी कट रहा है, नीचे फुल स्क्रीन नहीं हो पा रहा है, anyway. So that's what we talked about. So we have the gyromagnetic ratio for electron will be given by minus E by 2me, and that is gyromagnetic or magnetogyric, whatever you may call it. So the same thing can be understood. So you have combinations, two possibilities that spin. So assume that this is moving in the same direction, orbital motion is the same, but the spin is inverted. So look at the direction of spin. If the spin is inverted, then so we have two cases. In one case, so when we apply magnetic field B, this was what I was discussing in the last class. Magnetic field apply किया हमने, और so it produces, so electrons, because of having a negative charge, we get magnetic moment induced which is in opposite direction to the applied magnetic field. So the two, अब आप देखिए, there are two tiny, so we can imagine a magnet in electron behaving like a tiny magnet, and the moment is both the magnetic moment which are in opposite direction to the applied magnetic field, so energy of this system is going to be high. Okay, when you imagine that this spin is in opposite direction, now it is a different spin. Here is the spin angular momentum, the orbital angular momentum were pointing in the same direction. Now suppose spin angular momentum is reversed. In this case what happens, one magnetic moment is pointing down, another magnetic moment for the electron is pointing upwards. So both these things, so you have reduced, the magnitude is reduced, so overall the energy will be low. So you have a high component of magnetic moment which was opposed to the field in the initial case, the energy was high. Now that is reduced to good extent, and you have aligned. So as you know, this magnetic field due to spin was larger in magnitude, and overall thing will be, this is getting aligned, almost situation like this that is coming. Okay, so direction is, so that is why you see it is having low energy. So fundamental concept of physics अगर आप apply करते हैं, you can reach there why it is having low energy. Okay, so what is the conclusion becomes that the magnetic dipole moments that are anti-parallel will be lower in energy, and so magnetic dipole moments of the two things, that is spin and orbital, and when they are parallel, this one will be higher in energy. So when we have spin angular momentum and orbital angular momentum, so that way, so this interaction between these two states, so effect of electron on the magnetic field, what will happen when no magnetic field is applied? The plus half state, minus half state, both are having same energy. But as soon as you apply magnetic field, there is precession that happens, that this vector, so electron is here, electron is a particle and it is already moving like this, and you curl your fingers and it is pointing like this. So this vector is now uh, moving around the this z axis. So that is the precessional motion of the vector that we can think of. And in another case, it will be making up a cone like this on the lower half of the picture. So हेलो, हाँ समीक्षा, हाँ हाँ, गुड इवनिंग. अच्छा, ठीक है. ओके, ठीक है, अभी मैं क्लास ले रहा हूँ, उसके बाद करते हैं. ठीक है. कहाँ था मैं? So magnetic moments is magnetic moment is proportional to angular momentum 1. So we can always write like this. So this is what we had discussed last class. So यहाँ से आपको clear है. So the Hamiltonian we write is the magnetic moment into the magnetic field. So this is, we are taking the dot product of the two, both are vectors, and so this is how we have to formulate it from looking at the formula. Gyro magnetic ratio from previous slide we have discussed, last class also we have discussed. So negative sign, this has a negative sign, that's why you were seeing over there the direction of magnetic moment is reverse. Okay, not in the same direction as the angular momentum. Okay, the same thing. So we take only the z component, the magnetic field is along z direction, taken to be along z direction. जो भी magnetic field apply करोगे externally उसको z लिया जाता है, ये convention है, इससे आसान हो जाता है काम, and that's what we follow. Okay, so z direction is taken to be the direction for any externally applied field. So the component of angular momentum which is lying along that direction of magnetic field will contribute to generating this magnetic moment. So that's what you have to consider. So only z component is required which is given by ml cross h cross. And similarly, if you analyze the same thing, you just parallelly you analyze for spin and you put ms h cross. What is this? किसी ने कुछ मैसेज भेजा है क्या? नहीं. So कहाँ पे था यार? So there was simple thing. So we are now taking it to very simple. Magnetic moment. So you have to only that component of magnetic moment which the angular momentum which is lying along the z axis, so mu z is only required. You consider that for all such interaction for calculation of energies, and you get there. Okay, so you substitute it. So you substitute the value of Lz, which is coming from ml h cross, and you have the expression for energy ready. Okay, now so we describe the new thing minus gamma e h cross as the Bohr magneton. फिर ये कट जा रहा है नीचे. So why it is getting, so this is the Bohr magneton EH cross by 2me, okay, which we have just, so ml mu b dot b naught. So similarly you can think of so this is for orbital motion. You can also think in a similar manner. You can go for uh, Bohr magneton, then so this is a fundamental unit for calculation of all the magnetic moments. Similarly, you can think of spin magnetic moment arising from s is equal to half quantum number, and so we have the expression for this, and only take the z component. So z component when you z direction, so just go along with that, take this z direction sz, so ms h cross, and then use that thing to apply over there. So only the z component is required for whole calculations. G factor was, so for alpha and beta, that is clockwise and anti-clockwise, we plus half is denoted as alpha, minus half, so ms values, so s is half, and s the spin quantum number s is half, and you can have ms values plus half or minus half. So based on that you can again calculate the energy for this with Bohr magneton. This is the Bohr magneton that we have indicated over here. Okay, and yeah, plus in the absence of magnetic field, if there is no magnetic field, B is 0, both have same energy, there is no difference. But as soon as you apply magnetic field, you will see that the difference will arise, and uh, yeah, we're sweeping the cone. So this Larmor frequency, the sweeping of the cone will happen, that will be dependent on a frequency that is given by this B naught is a factor, so higher the magnetic field, greater will the Larmor frequency. For typically for a field of 1 Tesla, you will find 30 gigahertz for this, for electrons. Spin quantum number of a nucleus, so when you are talking about a nucleus, usually we talk of simplest case, it is, you can talk of proton, but in a nucleus you have a combination of neutrons and protons, so both are magnetic, both show magnetic property. An isolated neutron also shows a magnetic property, it has a magnetic moment, finite magnetic moment. You remember this thing. So together, taking nucleus as one particle, we can define a new set of spin quantum number I, that is already discussed in case of uh, Raman and FTIR. So you know the formalism of I. So it also follows the MIH cross is the component, which can range from I to I minus 1 plus I to minus I. So finally, this is what you get for protons. If you have protons and number of neutrons, even 0, you do, and so only those nuclei will contribute, will have a net angular net magnetic moment which is having odd numbers. Okay, any odd number will give you, so odd combination gives you integer multiple, so I can be 1 2 3 like this, or even odd combination will give you half integers and like this. So finally you can calculate for this also, और ये इस तरह से आपके पास आ जाएगा. So simple thing that you can think of nitrogen, oxygen. So nitrogen has 7 plus 7, so I is equal to 1. A proton has I is equal to half, you know this. both carbon and oxygen have I is equal to 0 magnetic moment, and so they do not respond. Magnetic field apply करो कुछ नहीं होगा. 16 oxygen 16 and carbon 12 C12 O16 do not respond to magnetic field. So magnetic moment mu. So in the way we have analyzed for this thing electrons, we can also analyze a similar thing with so the analysis that we have done with electrons, we can exactly in a similar way we can apply the concept, and mu is, there will be a gyromagnetic ratio into this I cap, which is the uh, angular momentum due to spin for the nucleus, and only the z component is to be taken for consideration. So you can have write mi h cross, and you are there, you have defined a Larmor you can find out the Larmor frequency for this. So you can in a similar fashion, so you have so Larmor frequency for this, the precession occurs around this cone that you have around the z axis along the cone, and for a 1 Tesla for proton, simply if you calculate, the field will come out to be the frequency will come out to be 40 megahertz. So see there that was around 30 gigahertz. Megahertz और gigahertz में अंतर आ रहा है इलेक्ट्रॉन वर्सेस प्रोटॉन. ठीक है. सो ये अब आपको डिफरेंस भी समझ में आ रहा होगा कि जब भी हम स्पेक्ट्रोस्कोपी करेंगे, we will be having electromagnetic radiation which will be corresponding to this megahertz for. So megahertz किसके रेंज में आता है? आप FM रेडियो सुनते हैं 100 मेगाहर्ट्ज 98 मेगाहर्ट्ज, ये सब आपका रेडियो फ्रिक्वेंसी है. रेडियो आप सुनते हैं, यू व्हेन यू लिसन टू रेडियो, ट्यून इनटू एफएम रेडियो, दैट इज द फ्रीक्वेंसी few megahertz. So that frequency is good enough to have a transition that to induce magnetic transitions. Okay, so this is an interesting point to be noted. And where in case of electron, you have a factor of 1000, almost a factor of 1000 is coming. Megahertz 10 to the power 6 and gigahertz 10 to the power 9. So that was the difference. So you will be using a much higher frequency electromagnetic radiations. So that will be माइक्रोवेव रेंज, दिस विल बी रेडियो वेव. मेगाहर्ट्ज तो आपको बिल्कुल आसानी से याद रह सकता है, आपकी एफएम की फ्रीक्वेंसी है वही, रेडियो ट्यून करते हैं तो इफ यू लिसन टू रेडियो. सो so the just similar to that, the way we have defined Bohr magneton for electron, we can also define Bohr magneton for nucleus mu n. Yeah, it is simple EH cross by M2MP. So you can also define in a similar way for nuclear magneton. So this is how we define it. So this is the mass of a proton that we can take for the simple analysis. So this is what we have to realize. If you have a proton which is having a magnetic moment, it is precessing around, when you apply the field B naught, it starts precessing along the cone, right? So that is so you imagine this vector, the pink color vector, is actually the right hand thumb rule you apply, and you are getting, so it is curling in a anti-clockwise fashion if you're looking from top. So then you have a thumb pointing in this direction, and then it moves. So you can think that motion is very complex kind of thing that we are talking about. The spin vector, and then that vector is precessing around the whole z-axis. So this is what happens. And now when you provide electromagnetic energy of right frequency, right energy, then that energy is absorbed and it gets aligned. Then it's opposing the field. So it was already precessing in the same direction as the field. So this was assuming you have a positive charge as here. Then this is what happens. But imagine if instead of a positive charge, if you have a negative charge such as electron, then what will happen? You apply the field, the natural tendency will be is to go. So for the same direction of the spin, you will have a different direction of the magnetic moment, opposite direction. So in that case, this will be reversed. Anyway, so so this is an important point. Even a neutron is having a spin. It has a magnetic moment, certain magnetic ratio. A G factor is also there associated with that. So G factor with proton. So this is the thing. Hydrogen, deuterium, C13, 14. So everything which is not zero, total spin quantum number is not zero, that will be magnetically active and will respond when you apply magnetic field. So the frequency, if you calculate, see at 1 Tesla, 29 megahertz, 42 megahertz, 6.5, like this. So so nuclear G factors vary between -6 to +6. Plus positive GI values and gamma denote a magnetic moment that is parallel to the spin. Negative values indicate that the magnetic moment. So negative G values you have here, positive values you can see here. So that indicate the magnetic moment and spin are anti-parallel. So that can happen. So this is the situation. So net energy you can think of, starting from here you can write it mi h cross b naught, and then you write it mu h cross as this gi mu n, which is the framework that we are adopting from taking example of electron. You had this kind of thing, so here also you can make up with Bohr magneton and gi, the G factor for nucleus. So we will put gamma is positive. We shall assume that gamma is positive, as is the case for majority of nuclei. For most cases you have this mu n is, this is having a positive. Okay, so you have nuclear magneton is about 2000 times smaller than Bohr magneton. This we have seen, and that's the reason that you are seeing the frequency is also around 1000 times, more than 1000 times different, and the mass also comes into picture. Energy of interaction with magnetic fields are about 2000 times weaker than electron spin angular momentum. So that's why for electrons you have resonant absorption in unpaired electrons. Okay, so unpaired electrons in the magnetic field. So what I was telling you, that what now we are talking about is an interaction of magnetic field with magnetic dipole. Previously, when we were talking about rotational spectroscopy or vibrational spectroscopy, we were talking about electric dipole interacting with the electric field. Now situation is different. So this is a fundamental difference between the spectroscopies, so that we are talking about. So अगर लाइट डाल रहे हो, उसका कौन सा पार्ट इलेक्ट्रिक फील्ड या मैग्नेटिक फील्ड इंटरेक्ट करेगा, वो यहाँ से पता चल रहा है. अगर उसमें मैग्नेटिक डाइपोल है, मैग्नेटिक part. So here we are concerned with the magnetic dipole of, we are treating the electrons as magnetic dipole. The proton is also a magnetic dipole, so they can interact with the magnetic field vector, and this is in the present in the light, present in the electromagnetic radiations. So that is what we are going to do. So minus half. So how the separation turns out to be, it is like this. So you can see this is, so for an, so if you have electron, So the plus half spin is lying higher in energy, and the minus half, एक minute. So just a moment, ये थोड़ा सा zoom in. हाँ, ऐसे देखो. So this is your alpha. So if you calculate the difference, energy of alpha, that is up spin, alpha is up spin, and energy of alpha minus the beta. So the separation when you apply magnetic field, so what we are talking about is this. See, when the magnetic field is off, the two plus half or minus half, no difference in energy. When you apply magnetic field on, then the minus half, which is spin having in this direction. So if the spin is pointing downwards, that will be lower in energy, because the magnetic field applied will align, it will be aligned with the field, so having lower energy. When you have plus half, the as this one, the spin momentum is pointing upwards, the magnetic momentum will be pointing downwards, so opposed to the field. So in that sense, you are having this kind of thing, and the difference in energy between the two you can calculate based on the above formula, the previous one that we have considered. E is given by ms mu b, so plus half minus half, you can substitute and get this. So the separation between this is dependent on the magnetic field. What you see here, a b naught terms is coming, so other things are constant, g e mu b. So higher the value of magnetic externally applied magnetic field, greater is the separation. And so beta state is lower, that is downspin vector, that the vector which is as compared to the alpha, because magnetogyric ratio is negative for electron. Remember, when it is proton, this gyromagnetic ratio is positive, and this order will be different. Beta will be higher energy, alpha will be lower. But the fundamental thing that you are noting, अभी भी आप fundamental चीज को पकड़ो, मैग्नेटिक मोमेंट जब भी अलाइन होगा मैग्नेटिक फील्ड के साथ, उस केस में एनर्जी कम होगी. जहां के सो अगर आप उस पॉइंट ऑफ व्यू से, फंडामेंटल पॉइंट ऑफ व्यू अगर आपने पकड़ लिया है, तो अभी भी आप वो दोनों के केस में सही होगा. ठीक है. So now if the sample is exposed to radiation of frequency mu, the energy separations come into resonance, and so if the frequency is matched, perfectly matched, the difference you are matching and giving that frequency of electromagnetic radiations, then the oscillating magnetic field vector in the light, in the electromagnetic radiation, will interact with this, with the magnetic moment of the electron, and absorption will occur. Electron will move to the upper level, that is ms plus half. ठीक है. So in a similar fashion you can define the thing for, so you have just learned about electron. So this kind of so there is a transition which is from beta to alpha, so minus half to plus half ms values, a strong absorption will occur if you provide the radiation. So this is called electron paramagnetic resonance. So you are achieving that condition for resonance, that is matching the frequency of the required for the electrons, so that Larmor precessional frequency that we were talking about, and at that point absorption will occur. So anything that is having unpaired electrons will show there will be absorption by observing the magnetic field at which. So you can learn about the molecules if they have unpaired electrons by observing these kind of transitions, absorption of light, absorption of the radiations. So magnetic field of about 0.3 Tesla, a very low magnetic field is required, 0.3 Tesla. So this is good enough to bring about the electrons in resonance, and this is typically used in a EPR, electron spin resonance, or ESR spectrometer. So having a wavelength of 10 gigahertz or wavelength of 3 centimeter inverse. So this is a typically 3 centimeter. The wavelength of 3 centimeter is typically a microwave radiation. So EPR is a microwave technique. And if you parallelly analyze the situation for nucleus, you have the separation here. It will be transition from alpha to beta. Alpha state will have uh, so nucleus, you can simply think of a proton to start with and spin half. So the case will be now reversed. When it is plus half spin up, the magnetic moment is also pointing up, and that is aligned. So alpha is in lower energy and beta is of higher energy. So the transition will be from alpha to beta in case of a nucleus, or simply said a proton. If you are thinking of a proton, so you are good. So you can see that here mu h cross b naught is the difference coming out to be, if you analyze the same way, same manner. So h mu must be equal to this thing. This is the condition. Resonance condition is this. Absorption occurs when this condition is achieved. You are the mu h b naught, which is the energy gap between these two states in a magnetic field on. So that equivalent amount of radiation must be provided having that frequency. So mu h b naught, gamma h cross b naught is the Larmor frequency of the nucleus. So Larmor frequency is matched by the frequency of the electromagnetic waves. So that way you are having, so mu is equal to mu L. That's how you are achieving this. So that's why we call it resonance. So this is the visualization of the things. So this is the spinning electron, anything. So a proton or an electron is a magnetic dipole having north pole and south pole like this, and plus half spin energy states for will be like this when you apply magnetic field. Without magnetic field, both are having same energy. So similar, in a simpler analysis like that we did for electrons, we can also think of applying a magnetic field, apply a magnetic field, the precession will start, and then you irradiate with some radio frequency region. We calculated to be few megahertz. So usually when you apply 12 Tesla, you have to give a 500 megahertz will be the radio frequency requirement, and the transition will occur from plus half to minus half. Mu h, so gamma h b naught is the frequency. So we consider spin half nuclei. NMR is applicable to nuclei with non-zero spin as well as protons, which are common. So spin half nuclei is 13C, 19F, 31P. So these are the things that will be important to us in addition to the hydrogen you have. So these are the things that, so we will discuss rest of the, so in the next few classes we will be discussing NMR in detail, the technique. So I stop here. We'll do this